All right, well, thank you for joining us today. This talk is titled IPv666 Address of the Beast. I am Marc, and this is Chris.
Hello.
And now allow us to reintroduce ourselves.
Hello.
I am a self-taught hacker. I do a lot of SDR hacking and reverse engineering and wireless vulnerability research. Until very recently, I was the other half of the red team at Snapchat. I've done a lot of DARPA challenges as a big hobby, and generally I just love learning how things work, taking them apart, and figuring out how they are broken.
Yeah, and hey, my name is Chris Grayson. I'm originally from Atlanta, Georgia. I've been in the security field for a little bit now, predominantly on the offensive side. So I've done quite a bit of penetration testing consulting, both full-time and part-time. I've had my own company doing attack surface enumeration, and most recently was working with Marc as part of the red team at Snapchat. I have since become fun employed, emphasis on the fun, not the unemployed. And yeah, that's me.
So the question we have here is, what are we talking about?
Willis.
And the answer is the future. And unfortunately, this animation isn't playing, but if it were, you would see this gentleman on the water-powered jetpack flying off of a yacht into the water, because the future is really a scary place. And I want to preface this talk by saying we are not network engineers. We've been learning about IPv6 over the course of the last year, so we'll probably get some stuff wrong about IPv6. If we do, please let us know. We look forward to learning more. So the future is a scary place. And in the future, we have IPv6, despite it being around for the last 23, 24 years. But in the last half a decade or so, IPv6 has been really growing in prevalence, and so it's something we need to spend more time thinking about. IPv6 is great from a number of degrees in that it's really improved upon some of the problems with IPv4. And over the last year, we've been gaining interest in IPv6 and specifically IPv6 security. And we have this hypothesis that there are likely devices and entire networks potentially exposed to the public internet over IPv6 as a result of automatic configuration and a lack of general understanding of IPv6. And so we wanted to start testing these hypotheses. So we started thinking about IPv6 security, and our initial idea was that, okay, we need to discover what these internet-facing IPv6 addresses were. And as far as we could tell, there weren't a lot of good ways to do this, and so to test our hypothesis, we've been working on mechanisms to actually discover internet-facing IPv6 addresses. So we're going to start with some background on IPv6 and our motivations for doing this research. We're then going to talk about the security implications of IPv6 as we understand them. We're going to talk about the difficulty with scanning the IPv6 address space, and then look at two different ways we've been accumulating addresses, both through honeypotting and from modeling to predict potential addresses. We're then going to talk about IPv666, which is the tool set we've released that you all will be able to use. So first, let's take a look at some background on IPv6. So what is IPv6 aside from being the future? So once upon a time, we only had IPv4, and we quickly learned that we were going to run out of IPv4 addresses. And despite having approximately 4.3 billion of them, we started running out pretty quick. And so we, as engineers, came up with something called network address translation, or NAT. And NAT allows you to have these private address spaces, such as your 10.star, 192.168.star, 172.16.star. And the premise is we can have these private networks which connect through a gateway which is routable on the public internet, but we can have multiple devices in these private address spaces in different private networks. Now, the intuitive way to deal with this problem of a lack of address space is to increase the number of addresses we have. And so IPv6 addresses this in a very simple way by increasing the address space we're looking at, going from 32 bits to 128 bits. And it also has a number of engineering improvements to address some of the problems with IPv4. So there's been this kind of common attitude that we don't need to care about IPv6 because nobody uses it, it's this esoteric thing, but lately that's become not the case. So this graph here shows us the percentage of users of Google who connect to Google via IPv6. This is spanning a 10-year period starting in 2009. And we can see in 2009, 2010, we had less than 1% or 2% of Google users connecting over IPv6. In 2013, 2014, this started to grow. And now in 2018, we have close to 25% of Google users connecting over IPv6. So this tells us that IPv6 is growing in prevalence and something that we actually need to be spending some time thinking about. And there are a number of things that IPv6 improves upon over IPv4. The packet headers are lower complexity, making it more efficient to process them. The routing is also simplified such that we have fewer hops required to route IPv6 packets versus IPv4 packets. The broadcast concept in IPv4 has been replaced by multicast in IPv6. So with IPv4, we have broadcast addresses to broadcast packets to the subnet mask and subnet of that specific address. In IPv6, we can do more granular multicast routing and specifying more granular endpoint destinations. But the big difference with IPv6 is we have this concept of automatic configuration where everything just works. So you can plug an IPv6 device into an IPv6 network. It will automatically assign an address to itself, find the nearest gateway, and configure routing. The scary part with this is we can have enterprises which configure networks to use IPv4, but because of this automatic configuration, they can actually have devices that are connected to the public internet over IPv6 and not having configured that at all, but still have these devices potentially reachable over the public internet. And so last year, we had a project with Chris and myself and our friend Logan, and we were doing some research into Comcast equipment and services. And we ended up finding a bunch of vulnerabilities, 26 CVEs that we presented at DEF CON last year. And through the course of that research, we discovered that we had a lot of vulnerabilities which were exploitable over IPv6, but only if we had knowledge of the IPv6 address of the device we wanted to attack. And this really got us thinking about the benefits of being able to actually enumerate this address space. And so I'm going to touch on two of the vulnerabilities to provide some context for why we had this interest. So if you are a customer of Comcast or any other ISP, and you need to contact customer service and have them investigate the current status of your equipment, the ISP needs to be able to connect to your equipment remotely. So in the case of Comcast, they have two security controls. We have credentials that are required to log into this administrative portal, and then we have a filter which only allows connections to the specific administrative portal if you are coming from an IPv6 address on Comcast infrastructure. So the credentials turned out to be hard-coded, and we were able to get those. But the difficulty was that in order to actually access this interface, we needed to connect over IPv6 from Comcast infrastructure. Comcast also has this service called Xfinity Send to TV. And the way this works, you go to the Comcast website, sign in with your credentials, you put in a URL into the website and hit go, and it instructs your set-top box to load a web browser and display the URL you put in a web browser on your TV. What we realized is that the way the network segmentation was set up, your set-top box was actually considered to be trusted Comcast infrastructure. So we could put in the IPv6 address of another customer's gateway into Send to TV. It would be rendered in a web browser on our set-top box. And because it was considered trusted Comcast infrastructure, we could sign in to any other customer's gateway and remotely configure it. And this was a pretty neat exploit, but it was only possible if we knew the IPv6 address of the gateway we were targeting. And so this is the first time that we really started to think about the benefits of being able to enumerate the public IPv6 address space. Now we have another IPv6 exploitable vulnerability on the Comcast set-top boxes. So everything that's displayed on the TV happens in a web browser, for example, rendering HTML5 video and streaming that over IP. If you are a Comcast engineer or a third-party app developer, you likely need to be able to debug the JavaScript code running in that web browser on the set-top box. In order to do this, they have a remote web inspector, which is functionally the dev tools for Chrome or Firefox. You can turn this on and connect over a TCP socket over the public internet and debug the JavaScript running on this web browser. To do this, you need to know the IPv6 address of that set-top box. So if we have knowledge of this IPv6 address, we can enable the remote web inspector through a Zigbee vulnerability we found and exploit some other vulnerabilities to execute code as a root user on the set-top box. So here we have two cases where we can remotely compromise a wide array of devices, but only if we know the specific IPv6 addresses of those devices. And now Chris is going to walk you through some of the security implications of IPv6.
Yeah, thanks, Mark. So yeah, we did this research. We found a lot of cool stuff. It was quite fun. And you know, we kind of got this notion that it's like, hey, these IPv6 addresses, they seem to be paying dividends. They seem to be something that could be a source of headaches for ISPs and whatnot. So, hey, let's look into this a little bit further. I'm going to preface this section with we are not network engineers, and this is what we've managed to accumulate in the kind of year that we've been looking at this. So we kind of started reading up on IPv6, found some things, we're like, oh, this sounds like it could be potentially problematic, and then went to the phase of let's validate these hypotheses, and that's where we really started the work that we're going to be talking about. So one of the first things that kind of made us raise an eyebrow is that you don't really have NAT anymore. NAT is network address translation. Whenever you take your laptop, join your home wireless network, you get a 10.star address, 192.168.172.1.6. That private address is coming from NAT. NAT is something that came out of the address exhaustion problem in IPv4. Prior to the RFC that created NAT, it was basically there was no such thing as private addressing, and this was a way to carve out these different address ranges so that various organizations could reuse the same network space. It was never intended to be a security control. But from my perspective, and I know this is a very hotly debated issue, I posted this on Reddit yesterday, and I'm getting torn apart for saying that NAT is a security control, but I still stand my ground. Basically, by default, when you have NAT, you're not going to be publicly routable, right? You can reach out to the internet, but the internet's not immediately going to be able to talk to you by default because you're actually on a private address space behind a public address. So you have to opt in to configuring NAT bypasses and NAT punch-throughs to enable traffic from the open internet to hit you. To me, that seems pretty nice. NAT in IPv6 does exist to the chagrin of IPv6 engineers, but it's no longer the default. So when you have your device and you put it on a network and you get an IPv6 address, that's going to be a publicly routable IPv6 address. You're not getting an address on a private network block anymore because private network blocks aren't the same as they were back in IPv4. There is something called unique local addresses, which fulfills roughly the same purpose as the private address space in IPv4. But until these unique local addresses are what you're getting by default when you join an IPv6 network, then what we see as the security improvements coming from NAT aren't going to be translated into IPv6. So the takeaway here is that in IPv6, when you get an IPv6 address, you're not immediately, basically, you are now routable. People can talk to you. Addresses are by default public and not unique local addresses. So another thing that we learned was that IP tables has nothing to do with IPv6. Fairly simple, but there's a completely separate binary and a completely separate rule table for IPv6-based firewalls. So if you've gone onto your VPS, if you've thought about it before and been like, I want to make sure that I'm protected on IPv6, I want to make sure that nobody can route traffic from me, IP tables -L, all right, sweet, my input chain is -J reject, everything's getting rejected, I'm safe. Well, it turns out that's not really the case because there's a separate binary, separate set of rules. So simple difference, all the commands are still the same, but a different binary that, our assumption is that people in their, people are creatures of habit, might not know about this. So these are slacks, not the sort of slack we're going to be talking about. What we're talking about is stateless address auto-configuration. And this is what Marc was talking about, where devices are able to provision IPv6 addresses for themselves without the assistance of another service. In IPv4, we have something called Dhcp, the Dynamic Host Configuration Protocol. And typically when you join an IPv4 network, unless it's managed in some other way, there's going to be a Dhcp server, and the responsibility of that server is to manage the IP address allocation within the network that it's currently in. So your device comes online, does a broadcast out for Dhcp, it gets a lease, says here's the IP address that you can have, here's how long that you can have it for, and now you've got an IP address that you can start communicating over. You don't need a Dhcp server in IPv6 because you have Slack. And what Slack is a protocol that defines a little song and dance that your device can do with all of the gateways that are on your local area network that enable you to automatically provision your own IPv6 addresses. So what is the takeaway here? Well, it's that if you have networking infrastructure that supports IPv6 and you have hosts that support IPv6, if you put them together, there's nothing else that you need to be provisioning in order for them to start communicating and start routing traffic over IPv6. So Slack has kind of been eclipsed by something called pslack, and that's the privacy extensions for Slack. Now, the way that Slack works, you kind of have your host bits and your network bits, which are differing parts of your IP address, and the interface identifier, which is the host bits, is derived from your MAC address. So in original vanilla Slack, you're basically going to take your MAC address and do a small permutation on your MAC address to fill out the interface identifier bits for your IPv6 address. This, might seem innocent on the surface, but people started thinking, hey, this is kind of bad. And so here's the scenario that they wanted to protect against. If you have your device open, you go to a website, let's say you're not logged in, you don't have cookies, whatever, but you're accessing some website, and you close your laptop, and you go to a coffee shop, and you open your laptop again. Well, the server is going to see requests coming from 2 different IPv6 addresses, but because of Slack, the MAC address of your device will be embedded in both of those IPv6 addresses. So even without cookies, without any other sort of tracking, just looking at the IPv6 addresses that are communicating with it, a server is able to say, hey, these different IPv6 addresses all came from the same device. Here's the different timestamps. This is where that person was, or where that device went. So they came up with something called privacy extensions for Slack. And what this does is it uses your MAC address and some other information to seed a random number generator, which is then used to create the interface identifier bits in pseudo-random fashion. So no longer do you have the MAC address embedded in the interface identifier. It's actually pseudo-random bits. And we're going to come back to that as a potential problem for IPv6 address discovery in a bit. So remember when I said that, if you take networking equipment that supports IPv6 and you take hosts that support IPv6 and you put them together, they can just start talking? Well, this is further compounded by the fact that IPv6 is the preferred communication protocol. So all modern networking equipment pretty much supports it out of the box, and all of modern operating systems support and prefer it. We read about this. We didn't really take it to heart to say oh yeah, everything's going to talk to us over IPv6 if they can. And so in some of our honeypotting, we took some extra steps to try and force people to talk to us or force devices to talk to us over IPv6. And then we found out that we are in fact idiots because they were automatically talking to us over IPv6 anyways. So your device, if your device can establish an IPv6 connection with whatever it's trying to communicate with, it's going to prefer that over IPv4. There's some other IPv6 related research which builds on top of this, where if there's not IPv6 enabled networking equipment and you're on a LAN with someone, you can basically imitate IPv6 networking equipment and start proxying their traffic because that's the connection they're going to prefer. It's pretty interesting stuff, not something that's in scope for what we're talking about today. Another thing that caught our eye is the many-to-one addresses to interfaces. So in my mind, with all the systems that I've administered, all the software that I've stood up, I regularly, what interface do you want to bind on? F0, whatever. And I choose that interface by looking at what my IP addresses are associated with those interfaces and picking the interface that is associated with the IP address that I want to bind on. And I've built this idea in my head that there's a one-to-one pairing between an IPv4 address and an interface. And this was kind of further grown through cases where it's okay, even if I throw VLAN tagging on my F0 interface, yeah, I'm going to get a new IP address, but at the operating system level, it's actually creating a second virtual interface. So if I do ifconfig, I will see a separate interface, S0:500, which is using the same physical interface, but again, at the operating system level, there's still this one-to-one interface to IP address pairing. I've learned, again, through the magical wonders of the internet, that I am wrong, and that you can actually put multiple IPv4 addresses on a single interface. It's not something that I've seen. Again, I'm not a networking engineer. But by default in IPv6, if you're going to have a publicly routable interface, you're going to have at least 2 IPv6 addresses on that interface. The FE80 address, which is your link local address, and whatever your public address is. You can have more than that as well. And to me, again, humans being creatures of habit, when in IPv4 you're largely used to saying, okay, well, I'm going to pick the interface that I'm going to listen on based on what IP address it's associated with, are people going to immediately understand that binding to a single interface is actually binding to a bunch of different IP addresses potentially? I don't know. Or I also don't know the syntax for if I want to have a protocol that's only going to be listening for link local traffic, how does it only listen to FE80? Is it just that we're specifying, here's the IPv6 address that I'm listening on? Or do I say this is the interface and the IPv6 address? Or do I say this is the interface and firewall off all the traffic that's coming to interface or to IP addresses that I don't want to be talking over? I don't know, but it sounds a bit more convoluted and a bit trickier than what people have had to deal with historically. This was a big one. My background is in penetration testing and breaking into things, and network penetration testing is one of the things that I enjoy doing the most. So when I hear ICMP, the only thing that I really associate that with is ping scans. ICMP stands for the Internet Control Message Protocol, or Management Protocol, and to me, when I hear that, it's like, oh, this must be very fundamental. This thing must be one of the bedrocks that the internet is built upon. But the only thing I've ever heard of ICMP and IPv4 being used for is ping scans. And so, general kind of knowledge around, well, how do you prevent ping scans? Well, disable it, firewall it off, whichever. My takeaway is that ICMP and IPv4 was not playing an ultra-critical role. That is not the case in IPv6. So in IPv4, we have ARP, the Address Resolution Protocol. It's a way that you can go from a layer 2 address to a layer 3 address, right? So go up the stack in the OSI model, enable you to start communicating at higher layers. We don't have ARP in IPv6. We have something very similar. It's called the Neighbor Discovery Protocol. It does effectively the same thing with a few minor differences, one of which is that it uses multicast instead of broadcast. But it's not its own protocol, its own wire protocol. It's built into ICMPv6. So whereas ICMP and IPv4 was something that was not, to my knowledge, fulfilling any critical roles, ICMP and IPv6 is something that if it's disabled across the board, you're not going to be able to route traffic. To me, that means that it might be harder to block ping scans. It might be more nuanced to actually make those sort of defenses work without taking your network down. And lastly, multicast is the new broadcast. So multicast did exist in IPv4. From my understanding, it was not widely used, and it was also a huge pain to get implemented and working correctly. And so those two put together meant that it's really not something that you saw very much. But in IPv6, it's baked into the protocol. So your networking equipment, if it's up to IPv6 spec, is going to have to support multicast. Again, like I said before, ICMPv6 is on top of multicast. So what is multicast? Well, it's a way to say, this packet is destined to this multicast address, and the networking equipment is going to know how to route that packet in such a way that is propagated to a certain distance and received by a certain type of party. So the first half of a multicast address dictates basically the propagation range. So you have different scopes like link local, only send it to all the devices on the local link. You have like site local, organization local, admin local. And then you have the global scope, which basically says propagate this packet ad nauseum. The other half of these addresses dictates the recipients. So you're able to say like, oh yeah, make sure that all of the SSDP devices receive this, or the MDNSV6 services receive this. I think the recipient group that raises my eyebrow the most is UPnP. So you could have a packet that says, propagate this as far as you can and make sure all of the UPnP services receive it. And UPnP is not particularly well known as being a bastion of security. So we read all of this. We have some varying level of understanding that these things might be kind of bad. And we say that, okay, this looks like something we should look into further. And then we start looking at how we actually start validating these hypotheses. But in summary, so IPv6 is going to work out of the box with minimal configuration. You're not going to have to put a DHCP server up for you to be able to start routing traffic. All of your devices and networking equipment support it and prefer it when possible. There's no such thing as private address space, with the caveat that there are unique local addresses. But again, until that becomes the default, it's not the same thing as we're dealing with in IPv4. Your existing firewall rules don't apply. The ones that you've administered over IP tables aren't relevant for IPv6. You can't prevent ping scans as easily as you do in IPv4, and single packets can be relayed to lots and lots of hosts via multicast in a way that is supported far beyond what happened in IPv4. So these are our assumptions. These are the hypotheses that we want to test. So now we got to find some IPv6 addresses to test it out.
And so now let's go hunting. So one of the big problems we have with IPv6 is this problem of scale. With IPv4, we have a 32-bit address space with 4.3 billion addresses. And that sounds like a lot, but in practice, a single host can do a TCP Connect scan across the entire IPv4 address space in an afternoon. And so while it's a lot of addresses, it is possible to completely brute force the address space. With IPv6, we have a 128-bit address space. And if you look at this number down here, this has 12 commas. And I don't know how to pronounce this number, but this is far more addresses than we could ever practically scan.
The internet told us it was 340 undecillion.
Undecillion. Good, good. And so pslack makes this problem a little bit harder. So if we want to predict addresses, we need addresses with low entropy. But pslack introduces entropy into the addresses. So as Chris explained earlier, when we're using slack or pslack, we're generating two parts of the address. We have the network bits, which represent what's equivalent to the subnet mask and subnet bits in an IPv4 address. And the network bits come from the gateway that the client is connecting through. In the case of Slack, the host bits are generated using the MAC address of the network interface. In pslack, however, we have a pseudorandom algorithm which generates high entropy host bits. Now this is going to be, in the case of the /IPv6, for example, 32 bits of entropy. And that entropy grows as the size of the network grows. And so because of this high entropy, we're not able to use modeling to predict pslack addresses. And so we really have two problems we're trying to approach when we want to identify addresses out in the wild. We have pslack addresses, which we reasonably can't model. And we have non-pslack addresses, which are either Slack addresses or addresses that are generated through some other addressing scheme. And so to address this pslack case, we decided to attempt some honeypotting to have clients connect to us instead of us predicting those client addresses. So we started with a DNS server, an SMTP server, and a web server. And we used a combination of organic mechanisms to have users visit our website, make DNS requests, or make SMTP requests. And then we used a marginally legitimate advertising company called Pop Ads to direct traffic to our website.
Totally legitimate.
Completely legit. So we started by setting up a bind DNS server on our server. And we have glue records pointing to IPv6. We have the name server itself resolving on both A records and quadruple A records over IPv4 and IPv6. And the premise is that we can have clients look up records from our name server over IPv4 or IPv6. And we have only quadruple A records for SMTP server and web server in an attempt to funnel users from IPv4 into IPv6. As we learned later, we didn't actually need that because of the preference for IPv6 with devices. But in this case, we were attempting to cause users to connect over IPv6. And so we had these services set up. We plastered these websites all over social media. We're not very popular, so that didn't work out terribly well. And then we paid for some traffic. So here we have a graph of our DNS requests over time. This is over the last 10 months. We have some spikes that are corresponding to the campaigns we ran with Pop Ads. And we're able to get a fair number of devices connecting to our DNS server over IPv6 and collect IPv6 addresses through that way. And a quick note on Pop Ads. So Pop Ads is the cheapest advertising network we were able to find, and we were able to pay 1 cent US per page view of our website. And this graph is showing our requests over a 120-second period. So we paid Pop Ads $50, the fire hose turned on, and we nearly immediately started getting requests at 500 to 600 requests per second. And we thought this was kind of suspicious because their claim was that these are actual users clicking on our website. This was, of course, not the case. We looked at one of the common refers that we saw, and it was an empty page with an anchor tag pointing to our site, and then a cryptocurrency miner in the background. So we don't have definitive evidence that this was malware or a botnet, but it was certainly a little bit suspicious.
And to be clear, there was no other indication on the page as to how that link got clicked. No other JavaScript, anything like that. Just the anchor tag and the crypto miner. So, yeah, who knows?
But that said, despite the fact that it was completely legitimate traffic, it provided a cost-effective way to get a whole bunch of client devices to visit our website and allowed us to collect some IPv6 addresses. So then on this server, we set up a honeypot web server at IPv6.exposed. We plastered this again all over social media, and the premise was we would get people to visit this website, we would collect those IPv6 addresses, and then on the site, we have a JavaScript web RTC payload, which will enumerate both the local IPv4 and IPv6 addresses of the network interface that is loading the website. With the IPv4 addresses, these are typically going to be the addresses on the local network behind that, so the 10.*192.168.*. And with the IPv6 addresses, these are going to be the internet routable IPv6 addresses of that network interface. So a user visits the page, the JavaScript payload executes, and then we post back those IP addresses to our data collection endpoint. And we had most success with this by generating traffic through pop ads. So here we have a graph of the traffic over time to the website. We have on the top the actual request to the web server itself, and on the bottom we have the JavaScript postbacks to our data collection endpoint for the web RTC payload. So it's hard to see on there, but the high point on the graph there on top is approximately 80,000 requests in each time period. And then for the web RTC invocations, we have only 3,000 or so on that same scale. And so what that told us is that while we were having a lot of devices request the website, less than 5% of them were actually executing the JavaScript payload, so it was likely more fraudulent traffic and not actual browsers loading this page in every case.
It's weird for a legitimate site.
Yeah, exactly. Completely weird. And then we had this brilliant idea, or so we thought, of setting up a honeypot SMTP server. And the premise was that we would have our email address on a lot of spam lists and plaster it over the internet and have people doing DNS lookups for the SMTP server, as well as trying to connect to it. We asked the Twitterverse what the best way is to get a bunch of spam addresses or spam accounts signed up to this email address. The consensus was to use a service called Mailbait. So we signed up for Mailbait, and the result was we had mostly devices that were actually email infrastructure doing the DNS lookups and SMTP requests. So we had a lot of communication from Hotmail and Yahoo Mail and Gmail, but not a lot of actual client devices. So this was us being optimistic, but finding out that it wasn't actually the best way to collect addresses. So what were the results from our honeypotting? Well, over the course of 10 months, we collected a little over 92,000 addresses, but it cost over $500 in infrastructure cost, and arguably it was kind of a lackluster way to do this. And one of the problems we've since learned is that ephemeral IPv6 addresses are likely the addresses we were collecting over WebRTC, and so we have a lot of these addresses, but a lot of them are probably not valid addresses that we can actually route to and connect to over the internet. So we kind of lost focus on this because it wasn't terribly exciting results and started this transition into the modeling, which Chris is going to take you through now.
Cool. So yeah, so we get all of the high entropy addresses out of the way, say that maybe we honeypot for them, maybe not. And honestly, the ephemeral addresses, to elaborate on them a little bit more. So thinking about a TCP connection, when you create a TCP connection with some remote service, your OS is going to pick an ephemeral port on your end to be connecting from, right? And you're not actually listening to anything on that port. Nobody can actually connect back to you with your IP address and port on that port. And so it's just this like one-time use connecting out sort of thing. And that notion has been brought over to IPv6, where the IP address that you're connecting back out through is also ephemeral. So it could very well be that honeypotting doesn't give you anything as far as like non-statically configured IP addresses go. But modeling is kind of interesting. So this is a list of IPv6 addresses that we took from public data sets, and we've removed all of the high entropy addresses that we had. And so if you blur your eyes a little bit, you might notice that you see some structure. They all start with the number 2, kind of the highest bits don't have as much entropy as the lower bits. There's various places where you'll regularly see various kind of like byte boundaries or nibble boundaries that you're going to see folks regularly using is where they delegate out new subnets, stuff like that. And this goes back to humans being creatures of habits, and also various kind of like learned practices, protocols, things like that, optimizations on the /64 boundary. But basically, the takeaway here is that when you remove the high entropy addresses, there's actually a decent amount of structure in the addresses that you're left with. So us being brilliant software engineers, how are we going to solve this problem? Obviously, blockchain. Just kidding. Machine learning, even better. So there's a picture up here of an eyeball. And it might be like, hey, this isn't a health summit. What are we doing here? Give me a second, because I'm not a machine learning expert. And this is how the concept of what we were trying to do with machine learning was explained to me. So if you look at an eye, you look at a lens, like, so you have like this input image of a candle, right? And in a perfect lens, when that image is projected through the lens, on the other side, you get the same as the input, just flipped, but that's not relevant for what we're talking about here. But the idea being that with a perfect lens, you have some sort of input, you pass it through the lens, and the output you get on the other side is an exact recreation of what you started with. So with the approach that we were taking with machine learning, we were trying to create an imperfect lens. The idea being that we're going to have some input data set, we're going to pass it through this lens, and this lens has an error rate. And this error rate isn't just randomly sampled. This error rate, it has errors that are representative of the structure of the data set that you built the model on, right? So the idea is you're making this compact representation of all the data that you fed into this model. It's going to have some sort of error rate. So when it does mess up this projection of data that you're putting through it, it's going to mess it up in a way that is reflective of the structure that the model learned from your input data set. So the way that this would work is we take all of the IPv6 addresses we had to train on, which was roughly like 7.5 million, pass them through, build this model of this lens, and then we, to generate 100,000 new addresses, we take 100,000 old addresses, pass them through the lens, the error rate does some sort of permutation on them, and gives us a bunch of new addresses to try scanning. Right? Sounds pretty cool, sounds pretty great, machine learning solves every problem. Yeah, nah, it actually didn't do anything for us because, again, we're not machine learning experts, but our colleague and friend that we were working with, he does this sort of stuff all the time, we couldn't get away from completely overfitting the model. Basically, our estimate is that there's actually such structure in IPv6 addresses that the model just learns it completely and creates a perfect lens. So try as we might, try like reconfiguring the different ways that we train the model. Every time we built this model, when we tried generating new addresses, we would say like, okay, here's 10,000 IP addresses, pass them through the model, and what did it do? It predicted our input set. So really not helpful, hence the Spider-Man meme. So we're like, okay, obviously we're idiots. We need to dumb things down a little bit. And we read a really cool paper, which is the Entropy IP paper. And it's a paper from, predominantly from Akamai and one other educational institute. But basically, they have access to all the IP addresses that went through the Akamai CDN, which is a ton. If I'm remembering correctly, it's like over 1 billion that they were able to analyze. And they looked into these addresses and found a lot of structure within them. I highly recommend checking out their website. They have these really cool graphics for the various networks that they've analyzed. But basically, they have a way to show that there are various relationships between different components of the IPv6 address. I want to say they use like Bayesian networks to show where those causalities are. And kind of the takeaway that we had from this was, hey, yeah, machine learning may not have worked, but there is lots of structure in here. People have done this. This is still kind of a bit more complicated than what we wanted to build. Our goal was to make something that everybody could use, just make it work front to back and have it be able to discover new IPv6 addresses. So we didn't go this far, but we made our own even dumber version. And this is what we did. So what we were trying to do, we wanted to build a probability distribution for every nibble in an IPv6 address for what the next nibble would be. So basically, we wanted to say, hey, for all of the IPv6 addresses that we've ever seen, when the first nibble is 2, what's the probability distribution for the next nibble? Or when the fourth nibble is 4, what's the probability for the next, the probability distribution for the next nibble after that? Because if we can map out what the probability distributions are for all the IPv6 address nibbles that we've ever seen, then we have at least some not completely random heuristic to say this is how we're going to generate new IPv6 addresses. And so we start with the IPv6 address up top. Let's see. That doesn't work at all. We start with the IPv6 address up top, we break it down into nibbles, and then basically we iterate over the nibbles, and we keep track of a counter. We say that, okay, in position 0, when the current value is 0x2, we've seen the next position be 0x8 one time, and increment that counter. In position 1, when the current value is 0x8, we see 0x0, increment that counter as the next nibble. do that for every single position, and we do that for every single IPv6 address that we have, and now we have probability distributions on a per nibble basis for every address that we've seen, dictating here's the likelihood of what the next nibble is going to be. So once we have that distribution, how do we actually generate a new IPv6 address? Well, all the addresses that we wanted to look into start with the nibble 2, just from spec. So we take a look and see, okay, for the probabilities for the 0th position with the value 2, what are they? And based on all the calculation that we've done, we know that here's the various probabilities of what the next nibble is going to be. So we create a 16-sided die, a weighted 16-sided die, roll that die, and however it rolls is going to be the nibble in our next position. So now we have the first 2 nibbles, and we go to the next index. We say, okay, for position 1 and value OXA, what are the probability distributions for the next one? Roll a weighted die, do it again, do that for all 32 nibbles in the address, and now you have an IPv6 address. This is by no means cutting edge compared to some of the other tech that's out there. There's a 6th-gen paper which is particularly cool, and the Entropy IP guys do something that's a bit different, but this is something that we built, and we were able to build based on publicly available data without privileged access. So, this is my favorite meme, and I'm super disappointed that it's not actually animating, but I would imagine that some of this audience has seen it before. But so we took this model, we initially wrote it in Python, and it was super slow, and then we wrote it in Golang, and it was like, wow, this is screaming fast. Everybody should write all their software in Golang forever. Just get rid of JavaScript. But we generated 10 million addresses using the statistical model, and then we scanned all 10 million addresses with ICMP probes, and we got like 50,000 responses. Like, oh my God, that's amazing. We totally solved this problem. We're great. We did it. False. Then we learned about another artifact of the IPv6 address world, which is Alias Networks. So I know that there's reasoning behind why Alias Networks exist. We're choosing to stick our head in the sand and just say because people are jerks, whoever's administering these networks. But what an alias network is that an entire network range responds to ICMP probes. So every single IP address in a range is going to appear to be live. That's not particularly good for IPv6 address scanning, especially not when we're building a statistical model. If we do these scans, and we start finding these alias networks, they're going to be overrepresented in the data set that we are collecting. When we take that data and feed it back into our statistical model, it's going to train towards those network ranges. So we actually found that basically, we got really excited because the first 50,000 worked, and then we generated another 10 million, and then we found 60,000. It was like, oh my gosh, it's getting better. And then it was like, by like 48 hours later, it's like, oh, we're all 10 million of them are live because they're all in this network range, and these are actually all the same host. So this was really problematic for a feedback loop that was training itself. So we had to figure out how to take care of these. And so here's what we did. So let's say that we do that ICMP ping scan, and this IP address we see at the top responded. We say, I don't trust you yet, IP address. You might be an aliased IP address. So what do? We wrap it in a /96 network. All right? So we're going to say, you know what? Maybe the rightmost 32 bits of this are aliased. We then generate 8 random addresses in that network. Right? So we're going to pick 8 addresses at random, because the likelihood that we're going to pick 8 addresses in a 32-bit address space, and all 8 of those are going to correspond to live hosts, is pretty low. It might happen. I don't think it's going to happen all that often. So we generate 8 addresses at random in that network range, and then we ICMP ping scan those as well. And we say if above a threshold of those addresses respond, that network is aliased, because there's no way that we guessed correctly. And so this is actually configurable in the software that we wrote. I think we generate 8 addresses and say if half of them respond, then yes, it's aliased. So now we know, okay, this /96 network is aliased, but it's pretty much guaranteed to be a smaller component of a larger network. So now the problem becomes, we need to figure out where the network boundary is. So how do we do that? Well, we actually do a binary search. So here's the address that we were scanning to begin with, and we say, okay, we know that you're in at least a /96 alias network, which means
that the rightmost 32 bits of this address are at least in the alias network. We don't know about the other 96 bits. So what do? We do a binary search on the bits that we don't know about. So these blue bits right here are actually flipped. So we take the right half of those 96 bits and flip them all. Because again, the idea with an alias network is that every address in the network is going to respond. So if those 48 bits are still in the network, then by flipping them, that should respond as well. So then we send a few probe packets to it and see what comes back. And we do one of two things. So after doing that probe, if no response is received, then that would indicate that the network boundary is somewhere in those 48 bits. And the 48 bits that we didn't test are certainly not aliased, right? So we have effectively said, okay, the leftmost 48 bits are not aliased, the rightmost 32 bits are, and the 48 that we tested, the network boundary is somewhere in there. So now we've reduced the search space that we're looking for. In the other case, when we do receive a response, we say, okay, then we know that these 48 bits are also part of the alias network. We add them to the group, so now we know that the rightmost 48 plus 70 bits are aliased. Did I do that right?
Yeah. So.
Yeah, whatever. You get it. So now we know the rightmost bits are aliased, and we don't know about the leftmost. Oh my God, I can't believe I'm so bad at this. 48, there we go. The leftmost we now need to look into. So we do this, we reduce the search space, and now we do it again, and we just do a binary search in this format. So we rinse and repeat. And it takes 5 to 6 iterations to go from a /96 to the specific network boundary of where the alias network resides. And it turns out that this actually works pretty well. I was pretty surprised by that and pleased. Which brings us to the coup de grace of the software that we wrote putting all of this together. We call it IPv666. It is on GitHub, so it's open source via GPL v3. And basically what this thing does is you can just kick it off, target it at the global network address space, or target it at a specific network address space, and it goes through this whole scanning loop, doing the generation, the network blacklisting, the alias network seeking, all of that stuff. It just does it for you, and then kind of gives you IPv6 addresses. So, our goal was the same way that you run Nmap with a ping scan and say, like, okay, cool, I want to get IP addresses. We wanted to recreate that same sort of experience in IPv6. So it comes with four different utilities: scan, alias, blgen, and clean. But here's how the actual scanner loop works. So first, it generates the addresses, however many you have configured. Second, it does that initial ICMP ping scan. Third, it groups all of the addresses that responded into those /96 networks. Fourth, it does that alias network seeking operation, so finding which of these networks are actually aliased and where are the network boundaries for those alias networks. 5, it takes the results and it adds them to the blacklist. And then 6, it takes all of the addresses that responded in step 2 and removes from that list the ones that are in alias network ranges. Once we have all of the actual real addresses that came out of it, we go to 7, where we take those addresses and update our statistical model with our findings. We then go to step 8, which is where we write the addresses to disk. Go to step 9, where we clean up all the files that we use to basically manage different things during the loop. And then it goes back to 1 and generates another set of addresses. And this actually works. So the 666 scan is probably the one that you'd be most interested in. This is the one that out of the box, you just point it and it starts scanning and generating addresses, going through that loop, and hopefully finding live IPv6 addresses for you. We have 666 alias. The purpose of this tool is just you give it an IPv6 network, and you want to say, hey, test to see if this is aliased, and if it is aliased, find the network boundary. So just doing that one operation that we were talking about of that binary search for the alias network range. We have blgen, which will take a list of IPv6 CIDR ranges and add them to your current network blacklist. So basically, if you know some networks that you don't want to be scanning, or know some that you don't want to be including in your results, you can use this to blacklist those networks. And then 666 clean will take a list of IPv6 addresses and remove from that list all of the addresses that are aliased or are in the blacklist that you either specify or that is found in the default location on disk. And so talk about this in the abstract, but how well does this actually work? So we finally got the software stable. It's running on a provider. Like the fact that our box isn't just falling over, we really appreciate it. When we targeted at the global address space, we throttled it to 20 megabits per second, which is not all that fast, and it ran for 8 days. And in those 8 days, 58,388 unique IPv6 addresses were found. Non-PSLAC, non-aliased, we found roughly 60,000 unique addresses. And the part that I really liked about this is we took this data and we looked against the addresses that we knew about already, and it turns out that roughly 80% of those addresses that we found were not in any of the public data sets that we had used. So the takeaway being that this is actually finding addresses that are not publicly, as far as we know, not publicly recorded right now. They don't have quadruple A records pointing to them. They're just IP addresses that are configured and somehow people are routing to them, maybe internal DNS. And then we were like, well, what if we target an address space? And so we picked one of the IPv6 addresses that we had found in the first step, did a whois lookup on it, and I promise this is completely random. Did a whois lookup on it, found that it was contained in the /48 that was owned by an Ecuadorian ISP, and we pointed the scanner at the /48 network that they had and ran it for 30 minutes, throttled it to 20 megabits per second, and in those 30 minutes, we found 4,901 IPv6 addresses that would respond to IPv6 probes. And then we looked at it a little bit further, and it was mostly consumer premise equipment, meaning that it was all consumer gateways that had login portals available over port 80. And then we started convulsing because of the flashbacks that we had from last year's research. So we have a blog post, which I'm continuing to update and edit based on feedback that I'm getting from the community. Right there. We also have the GitHub repository. This will be, I believe these slides will be sent out through the conference as well as through our various Twitter accounts. But that's where the software is. We highly encourage you to check it out and use it. If you have any feedback, please let us know. And Marc's going to wrap things up with a conclusion.
So in recap, we started by providing background information on IPv6 and our motivations for doing this work. We took a look at the security implications of IPv6, discussed the scanning problem with this massive address space. We then looked at the honeypotting techniques we use to attempt to discover PSLAC addresses and the modeling techniques for non-PSLAC addresses, and then discussed IPv666, which is a tool set that is now available to you open source. There are some prior art that we'd like to reference. We have Entropy IP, 6gen, the paper clustering of IPv6 address structure, and then the IPv6 hitlist project. Some very great work. We recommend you check it all out. And now we have time for some Q&A.
Are there any questions from the floor?
Yep.
So thank you. First of all, great talk. Really enjoyed it. In the scanning, when you probed for the alias addresses, I saw you started with a /69 and worked from there. Did you consider taking the /64, which is the default subnet in IPv6, as normal boundary? Because any network engineer who configures a /69 should be shot or fired, or both.
So, of the various things that we have learned since posting all this stuff online, we actually did not know that /64 was such a meaningful boundary, and it's like RFC 6000 whatever. So that was unknown to us. We had actually previously used /64 as the boundary, but we didn't do the boundary seeking after that. So we kind of had organically come to this conclusion that /64s clearly weren't cutting it, because our blacklist grew to 30 million plus /64s. So that's one of the places that we'd like to improve this software. But yes, we're not doing it right now. It's a place that we have recently learned about and we'll hopefully update.
Are there any further questions? No? All right. Then thank you very much, guys, and enjoy your lunch, everybody.
Yep. Thank you all.
Yep, thank you.